CIET NCERT presents audiobook Ganit Manjari Part 1, Textbook of Mathematics for Grade 9.
Chapter number 3, page number 41. The World of Numbers. On the top right corner of the page, you are provided with a QR code, scanning which you can reach out to the additional resources to this chapter. 3.1 The Dawn of Mathematics. The Human Need to Count. Long before humanity built cities, formulated laws, or studied the stars, there existed a fundamental practical necessity, the need to keep count. Mathematics did not begin in a classroom with equations on a board. It began in the dirt, on the bark of trees, and on bones. Imagine you are living thousands of years ago in a small agricultural settlement along the banks of the Saraswati River. You have a herd of cattle. Every morning they go out into the dense forest to graze, and every evening they return. How do you ensure that a calf has not wandered off? Without words for numbers and without written symbols, early humans solved this through a concept called one-to-one correspondence. For every cow they left the settlement, the herder might place one pebble in a clay pot. In the evening, for every cow they returned, one pebble was removed. If the pot was empty at the end of the day, the herd was safe. If pebbles remained, cows were missing. This simple act of matching one object to another was the birth of the natural numbers. N is equal to 1, 2, 3, 4, and so on. 3.1.1 A history written in bone. While the decimal place value system we use today was perfected in the Indian subcontinent, the earliest physical evidence of humanity recording natural numbers takes us deep into the heart of Africa. The first mathematicians did not use paper. They used tally marks carved into bone. The Libombo bone, discovered in the Libombo Mountains between South Africa and Swaziland, dates back approximately 35,000 years. It is a bone featuring 29 distinct, deliberately carved, uniformly sized notches. Anthropologists and mathematicians believe this was not just random scratching, but a tool used as a lunar phase counter or a menstrual calendar, indicating that early humans were tracking time through natural numbers. Page number 42. Even more fascinating is the Ishango bone, found near the headwaters of the Nile River in the Democratic Republic of Congo, dating to around 20,000 BCE. This bone contains 3 columns of asymmetrical notches. What makes the Ishango bone a mathematical marvel is the specific grouping of the tallies. One of the columns groups notches into 11, 13, 17, and 19, the prime numbers between 10, and 20. Another column seems to demonstrate the concept of multiplication by 2, that is doubling. These artifacts indicate that the abstract concept of a number is indeed tens of thousands of years old. Here we have a picture in which representation of the prime numbers tally groupings found on the Ishango bone have been depicted in the figure 3.1. In this figure, we can find on one side 11 tallies marked on the bone. Then towards the upper part, we have 13 tallies marked on the bone, and on the lower side we have 17 tallies marked, and again on the upper end we find 19 tallies marked on the bone. 3.1.2 The Indian context, trade and astronomy. As civilizations advanced, so did the need for larger numbers. In the ancient urban centers of the Indus Valley civilization, such as Lothal and Harappa, standardized weights and measures were crucial for trade. A merchant trading terracotta pottery, lapis lazuli, or cotton with Mesopotamia needed a robust system of accounting. During Vedic times, Indian philosophers were fascinated by and deeply pondered large numbers. In the Vedas, which go back thousands of years, names were given to all powers of 10 up to 10 to the power 12, which was called Prarardh. In the Lalit Vistar, in the 4th century BCE, Buddha describes names up to 10 to the power 53, which is called Talakshan. Expressing quantities in terms of powers of 10 was explicitly used in the Rigveda, thus setting the stage for the number system based on powers of 10 to be developed in India in the ensuing years and which we now use around the world today. The development of the Indian numeral system in terms of place values and powers of 10 also helped pave the way for what is perhaps the most important mathematical invention in human history, the concept of zero. Page number 43. Exercise set 3.1. Question number 1. A merchant in the port city of Lothal is exchanging bags of spices for copper ingots. He receives 15 ingots for every 2 bags of spices. If he brings 12 bags of spices to the market, how many copper ingots will he leave with? Question number 2. Observe the sequence of numbers on one column of the Ishango bone 11, 13, 17, 19. What do these numbers have in common? List the next 3 numbers that fit this pattern. Question number 3. We know that natural numbers are closed under addition. The sum of any 2 natural numbers is always a natural number. Are they closed under subtraction? Provide a couple of examples to justify your answer. Question number 4. Ancient Indians used the joints of their fingers to count, a practice still seen today. Each finger has 3 joints and the thumb is used to count them. How many can you count on one hand? How does this relate to the ancient base 12 counting systems. 3.2 The revolution of Shunya, when nothing became something. For millennia, a number line started at 1. If you had 5 apples and gave all 5 away, you did not have a number to represent your state. You simply had a void, a lack of apples. Civilizations like the Babylonians and Mayans used placeholders, symbols to indicate an empty column in a number, but they did not treat nothing as a number that you could add, subtract, and multiply. It was in the work of Brahmagupta 628 CE that the void was formally transformed into a number, which truly transformed mathematics. This monumental leap was in turn inspired by Indian philosophical traditions. 3.2.1 From philosophy to mathematics. The concept of shunyata in the Upanishads and in the vast Buddhist literature starting well before the 7th century BCE, the concept of shunyata, emptiness or nothingness, was a profound state that was the goal of a yoga and meditation. Page number 44. The word shunya means zero, and the word shunyata, zeroness, was used extensively in these works to describe the state that one is trying to reach during meditation, that of emptying one's mind of all vritti in fluctuations of the mind. To achieve the state of perfect stillness and tranquility, Patanjali in the Yoga Sutras around the 3rd century BCE also describes how shunyata can help lead to control over one's mind, body, and senses. Because Indian thinkers revered this state of emptiness, they possessed the conceptual framework necessary to welcome nothingness as a concept in philosophy. This concept of zeroness then found its way into many fields such as architecture, literature, linguistics, and eventually made its way into mathematics in the works of Aryabhatta and finally Brahmagupta. Thus, the philosophical concept of emptiness crystallized into the mathematical zero. 3.2.2 The Bakshali manuscript and Brahmagupta's rules. In the Hindu number system that we use today, the physical transition from a blank space to a symbol can be seen in the Bakshali manuscript. Dated to the early centuries CE, it features a bold dot, bindu, used to represent zero. However, a symbol is just a mark on a page until it has rules. The transformation of zero into a fully operational number occurred in the work of Brahmagupta. In his seminal work, the Brahma Sputa Siddhanta 628 CE, he explicitly defined zero as the result of subtracting a number from itself. A minus A is equal to 0. Brahmagupta then laid down the fundamental laws of arithmetic with Shunya. Brahmagupta's rules for zero. First one, when 0 is added to a number, the number remains unchanged. A plus 0 is equal to A. Second one, when 0 is subtracted from a number, the number remains unchanged. A minus 0 is equal to A. Third one, when any number is multiplied by 0, the result is 0. A into 0 is equal to 0. Page number 45. 3.3 Integers expanding the horizon. Brahmagupta did not stop at 0. He realized that if subtraction of a number from itself can result in 0, 5 minus 5 is equal to 0, then what would happen if we subtract a larger number from a smaller one? 3 minus 5 is equal to dash. To answer this, Brahmagupta grounded his mathematics in the reality of commerce and life. He recognized two states: fortunes, that is dhan, positive numbers representing wealth or assets, debts as rin, negative numbers representing debts. By moving to the left of 0 on the number line, Brahmagupta formally introduced negative numbers to the world. The combination of positive natural numbers, their negative counterparts, and 0 creates the set of integers denoted by the symbol Z. From the German word Zahlen, meaning numbers. Here, in figure 3.2, we have a picture of a number line which ranges from -4 to +5 as -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. 0 is shunya in the center, and fortune, that is dhan, moves towards right side of the number line with positive integers, and debt, that is ren, represented by negative integers, moves from 0 to left on the number line. 3.3.1 The arithmetic of integers. Brahmagupta gave explicit rules for adding and multiplying these integers, which we still use exactly as he wrote them over 1300 years ago. First one, a fortune plus a fortune is a fortune. 5 plus 4 is equal to 9. Second one, a debt plus a debt is a debt. -5 plus -4 is equal to -9. If you owe 5 rupees and borrow 4 rupees more, you owe 9 rupees. Third point, a fortune minus 0 is a fortune. A debt minus 0 is a debt. 7 minus 0 is equal to 7, and -6 minus 0 is equal to -6. Fourth one, the product of a debt and a fortune is a debt. -3 into 4 is equal to -12. If you take on 4 debts of 3 rupees, your total debt is 12 rupees. Fifth point, the product of two debt is a fortune. -3 into -4 is equal to 12. Page number 46. Think and reflect. Why does a negative times a negative equal a positive? Think of it in terms of action and depth. If a negative number represents a depth, then multiplying by a negative number represents the removal of that debt. Hint: if someone takes away minus sign in brackets 4 of your debts that are each worth 3 rupees, that is minus 3 within brackets, you are effectively 12 rupees richer. Therefore, minus 3 into minus 4 is equal to plus 12. Exercise set 3.2. Question number 1. The temperature in the high altitude desert of Ladakh is recorded as 4 degrees Celsius at noon. By midnight, it drops by 15 degrees Celsius. What is the midnight temperature? Second question. A spice trader takes a loan, that is debt, of 850 rupees. The next day, he makes a profit, that is fortune, of 1200 rupees. The following week, he incurs a loss of 450 rupees. Write the sequence as an equation using integers and calculate his final financial standing. Question number 3. Calculate the following using Brahmagupta's laws. First part, minus 12 into 5. Second part, minus 8 into minus 7. Third part, 0 minus within brackets minus 14. Fourth part, minus 20 divided by 4. Question number 4. Explain using a real-world example of debt why subtracting a negative number is the same as adding a positive number. Example: 10 minus within brackets minus 5 is equal to 15. 3.4. Filling the spaces, fractions and rational numbers. As society grew more complex, measuring became just as important as counting. If a farmer divides a field of wheat among his 3 children, how much does each get? If a recipe calls for half a cup of ghee, how do we represent that mathematically? Numbers that represent parts of a whole are called fractions. Just as every natural number has an additive inverse, 3 has minus 3, 19 has minus 19, etc. We can conceive of additive inverses for every positive fraction. Minus 3 upon 4 for 3 upon 4, minus 19 upon 7 for 19 upon 7, etc. Let us refer to such additive inverses of positive fractions as negative fractions. Page number 47. Note that in a negative fraction, the minus sign can also be placed with either the numerator or denominator as follows. Minus 1 upon 5 is equal to minus 1 upon 5, that is equal to 1 upon minus 5. When we combine all integers and all fractions, both positive and negative, we get the set of rational numbers denoted by Q for quotient. A rational number is defined as any number that can be expressed in the form P upon Q, where P and Q are integers and Q is not equal to 0. Think and reflect. Can you explain why we need Q not equal to 0 in the definition of a rational number? We must make some important observations at this stage. All rational numbers can be written in the form P upon Q where p and q are integers and q is not equal to 0. For example, 5 and minus 10 can be written as 5 upon 1 and minus 10 upon 1 respectively. What this means is that the rational numbers also include the natural numbers, whole numbers, and integers. Rational numbers do not have a unique representation in the form p upon q, where p and q are integers and q is not equal to 0. For example, we have minus 1 upon 3 is equal to minus 2 upon 6 is equal to minus 3 upon 9 is equal to minus 10 upon 30, that is equal to minus 2026 upon 6078, and so on. These are equivalent rational numbers or equivalent fractions. This fact allows us to freely divide any common factor between the numerator and the denominator of a given fraction. The resulting fraction is then equivalent to the original one. For example, 12 upon 30 is equivalent to 2 upon 5. Here, we have divided both the numerator and the denominator by 6. The common understanding is that when we say that p upon q is a rational number, or when we represent p upon q on the number line, we assume that q is not equal to 0 and that p and q have no common factors other than 1, that is, p and q are co-prime. Page number 48. So, on the number line, among the infinitely many fractions equivalent to 1 upon 2, that is the fraction 1 upon 2, 2 upon 4, 3 upon 6, 6 upon 12, and so on, 1013 upon 2026, and so on. We choose 1 upon 2 to represent all of them. As you will remember from grade 6 and 7, Brahmagupta also gave rules for addition, subtraction, multiplication, and division of fractions. He noted that these rules also apply to both positive and negative fractions, which together constitute the rational numbers. Here are the various laws. First one, equality. Two rational numbers, a upon b and c upon d, are said to be equal if a into d is equal to b into c. Second one, addition and subtraction of two rational numbers. We first express the two rational numbers as fractions a upon b and c upon b with the same denominator b. Then we use the rules a upon b plus c upon b is equal to a plus c upon b and a upon b minus c upon b is equal to a minus c upon b. Third one, multiplication and division of two rational numbers. We use the rules a upon b into c upon d is equal to a into c upon b into d, provided that b is not equal to 0 and d is not equal to 0, and a upon b divided by c upon d is equal to a upon b into d upon c, that is equal to a into d upon b into c, provided that b is not equal to 0, d is not equal to 0, and c is not equal to 0. Fourth one, with the arithmetic laws defined as above, addition and multiplication are both commutative. that is A upon B plus C upon D is equal to C upon D plus A upon B, and A upon B into C upon D is equal to C upon D into A upon B, and they follow the law of distributivity. If P, Q and R are rational numbers, then P into within brackets Q plus R is equal to PQ plus PR. Rational numbers are closed under addition, subtraction, and multiplication. That is, if one adds two rational numbers or subtracts two rational numbers or multiplies two rational numbers, a rational number is again obtained. Rational numbers are also closed under division, provided that one does not divide by 0. That is, the quotient of two rational numbers is again a rational number as long as one does not divide by 0. Page number 49. Think and reflect. Question number 1. While adding or subtracting two rational numbers having different denominators, how will you make the denominators equal? Question number 2. Verify the distributive law for rational numbers. Exercise set 3.3. Question number 1. Prove that the following rational numbers are equal. First part, 2 upon 3 and 4 upon 6. Second one, 5 upon 4 and 10 upon 8. Third one, minus 3 upon 5 and minus 6 upon 10. Fourth one, 9 upon 3 and 3. Question number 2. Find the sum. First part, 2 upon 5 plus 3 upon 10. Second part, 7 upon 12 plus 5 upon 8. Third part, minus 4 upon 7 plus 3 upon 14. Question number 3. Find the difference. First part, 5 upon 6 minus 1 upon 4. Second part, 11 upon 8 minus 3 upon 4. Third part, minus 7 upon 9 minus within brackets minus 2 upon 3. Fourth question, find the product. First part, 2 upon 3 into 3 upon 10. Second part, 7 upon 11 into 5 upon 8. Third part, minus 4 upon 7 into 5 upon 14. Question number 5. Find the quotient. First part, 2 upon 3 divided by 3 upon 10. Second part, 7 upon 11 divided by 5 upon 8. Page number 50. Third part, minus 4 upon 7 divided by 5 upon 14. Question number 6. Show that 1 upon 2 plus 3 upon 4 within brackets into 8 upon 3 is equal to 1 upon 2 into 8 upon 3 plus 3 upon 4 into 8 upon 3. Question number 7. Simplify the following using the distributive property. 7 upon 9 within brackets 6 upon 7 minus 3 upon 4. Question number 8. Find the rational number x such that 5 upon 6 within brackets x plus 3 upon 5 is equal to 5 upon 6 into x plus 1 upon 2. 3.4.1. Representation of rational numbers on the number line. We already know that integers can be represented on a number line. To do this, we first choose a point and mark it as 0, called the origin. Moving 1 unit to the right gives the point representing 1. 2 units to the right gives 2, and so on. Similarly, moving 1 unit to the left of the origin gives -1, 2 units to the left gives -2, and so on. Each integer lies at an equal distance from the next one. This is represented in figure 3.3. Here we have a picture in which we can find figure 3.3 representing a number line with the integers marked on it. We have 0 at the center, and towards the right we have the integers 1, 2, 3, 4, 5, 6 and 7. And towards left of 0, the numbers marked here are -1, -2, -3, -4, -5, -6 and -7. Rational numbers can also be represented on the number line. Unlike integers, they may lie between two integers. For example, 1 upon 2 lies exactly halfway between 0 and 1, and -3 upon 4 lies between -1 and 0 as displayed in the figure 3.4. Here we have picture of figure 3.4 on which we can see a number line and 0 is at the center, and towards the right we have the markings as 0, 1 and 2, and 1 upon 2 is marked in between 0 and 1. And towards the left we have 0, -1 and -2, and we can find the marking of the point -3 upon 4 between 0 and -1. To represent a rational number p upon q, q not equal to 0 on the number line, divide the unit interval, the distance between two consecutive integers, into q equal parts. Then move p parts from 0 to the right if the number is positive and to the left if it is negative. Page number 51. For example, to represent 3 upon 4, divide the interval between 0 and 1 into 4 equal parts and move 3 parts to the right from 0. In figure 3.5, we have a picture of a number line starting from 0. We have 3 markings between 0 and 1, namely 0, 1 upon 4, 1 upon 2, 3 upon 4 and 1. Even fractions greater than 1 can be located on the number line in this way. For example, 9 upon 4 is equal to 2 whole 1 upon 4, so it lies between 2 and 3. We divide the interval between 2 and 3 into 4 equal parts and move 1 part to the right of 2. Observe figure 3.6. In this, we have a figure which represents the numbers between 0 and 3. We have the markings as 0, 1 upon 4, 1 upon 2, 3 upon 4, 1, 5 upon 4, 3 upon 2, 7 upon 4, 2, 9 upon 4, 5 upon 2, 11 upon 4 and 3. Think and reflect. Try and represent 8 upon 5 and -7 upon 4 on a number line. Here we have a picture of figure 3.7, some integers and rational numbers on a number line. We have a number line here on which the markings range from -5 to +5 as -5, -4, -3, -2, -1, 0, 1, 2, 3, 4 and 5. We find -22 upon 5 placed between -5 and -4, and minus 18 upon 5 is marked between minus 4 and minus 3, and minus 9 upon 4 is marked between minus 3 and minus 2. Minus 7 upon 8 is marked between minus 1 and 0. 7 upon 8 is marked between 0 and 1. 3 upon 2 is marked between 1 and 2. 9 upon 4 is marked between 2 and 3. 26 upon 7 is marked between 3 and 4. 32 upon 7 is marked between 4 and 5. Absolute value of a rational number. The absolute value of a rational number x, written as x between the two bars, represents its distance from 0 on the number line. Example 1. Absolute value of 5 upon 3 is equal to 5 upon 3. Absolute value of minus 5 by 3 is also equal to 5 by 3, and absolute value of 0 is equal to 0. Thus, the absolute value of a positive number is the number itself. The absolute value of a negative number is its positive value. Therefore, the absolute value of any rational number is always non-negative. That is, absolute value of x is always greater than or equal to 0. Page number 52. For two rational numbers a and b, the distance between them on the number line is given by absolute value of a minus b. Figure 3.8 represents the distance between the integers minus 4 and 3. Here in figure 3.8, we have a picture of a number line with markings ranging from minus 5 to plus 4 as minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3 and 4. And there is an arrow marked between minus 4 and 3. Minus 4 is represented by B and 3 is represented with A. And the arrow is the representation of the distance between A and B, represented as absolute value of A minus B is equal to 7. 3.4.2. The density of rational numbers. One of the most magical properties of rational numbers is that they are dense. Between any two integers, say 1 and 2, there is a rational number 3 upon 2. Between 1 and 3 upon 2, there is another rational number 5 upon 4. No matter how close two rational numbers are on the number line, you can always find another rational number between them by taking their average. For example, a rational number between 1 and 3 upon 2 can be found by taking their average. 1 plus 3 upon 2 upon 2, that is equal to 5 upon 4. Try to explain why. The average of two rational numbers a and b, which equals a plus b upon 2, is always a rational number between a and b. Here we have figure 3.9, which reflects a number line with the markings 1 and 2, and we have numbers 5 upon 4 and 3 upon 2 marked between 1 and 2. This means that there are infinitely many rational numbers between any 2 points. It feels as though the rational numbers must completely fill the number line, leaving no gaps whatsoever. But do they? Exercise set 3.4. Question number 1. Represent the rational numbers 2 upon 3, minus 5 upon 4 and 1 whole 1 upon 2 on a single number line. Question number 2. Find three distinct rational numbers that lie strictly between minus 1 upon 2 and 1 upon 4. Page number 53. Question number 3. Simplify the expression minus 1 upon 4 plus 5 upon 12. Question number 4. A tailor has 15 whole 3 upon 4 meters of the fine silk. If making one kurta requires 2 whole 1 upon 4 meters of silk, exactly how many kurtas can he make? Question number 5. Find three rational numbers between 3.1415 and 3.1416. Question number 6. Can you think of other ways to find a rational number between any two rational numbers? 3.5 irrational numbers. For centuries, mathematicians believed that every measurable length in the universe could be represented as a ratio of two integers. However, when Bodhaina composed his Sulba Sutra, a manual for constructing complex geometric fire altars in around 800 BCE, he quickly encountered lengths that defined fractions. The ancient Greeks encountered the same crisis a few centuries later. Consider a square where each side is exactly 1 unit long. By the Bodhaina Pythagoras theorem, the length of the diagonal D is given by 1 square plus 1 square is equal to D square, or D square is equal to 2. Therefore, the length of the diagonal is square root of 2. Here we have in figure 3.10 picture of a square having sides of 1 unit, and the diagonal is represented with square root 2 along the side. Here we have in picture a square with side 1 unit, and diagonal is represented with square root 2. Think and reflect. Can square root 2 be written as a rational number p upon q? As you learnt in grade 8, the answer is a resounding no. We will soon again see why. Numbers on the number line that cannot be expressed as a ratio of integers are called irrational numbers. 3.5.1. The proof of irrationality of square root 2. The first proof of the irrationality of square root 2 is due to a mathematician named Hipparchus, who was a member of the Pythagorean school c. 400 BCE. To explain why square root 2 is irrational, he employed a brilliant technique called proof by contradiction. Page number 54. Namely, we assume the opposite of what we want to prove and show that this assumption leads to a logical disaster. Proof. We shall explain the proof in steps. Step 1. Assumption. Assume square root 2 is a rational number. Therefore, it can be written as a fraction p upon q, where q is not equal to 0 in its simplest form. This means p and q are integers that share no common factors other than 1. That is, they are coprime. Square root 2 is equal to p upon q. Step 2. Square both sides of the equation. 2 is equal to p square upon q square. Step 3. Multiply both sides by q square. 2q square is equal to p square. Step 4. Deduction for p. Because p square is equal to 2 times some integer, p square must be an even number. If the square of a number is even, the number itself must be even. Therefore, p is an even integer. Let us say p is equal to 2k, where k is an integer. Step 5. Substitute p is equal to 2k back into our equation from step 3. 2q square is equal to 4k square. Step 6. Divide both sides by 2. Q square is equal to 2k square. Step 7. Deduction for q. Now we see that q square is equal to 2 times some integer k. This means q square is even and therefore q must also be an even integer. Step 8. The contradiction. We deduced that p is even and q is even. This means they both share a common factor of 2. However, in step 1, we stated that p upon q was in simplest form, sharing no common factors. Page number 55. Because our logical steps are flawless, our initial assumption must be wrong. Therefore, square root 2 cannot be expressed as a fraction. It is irrational. Here we can find a picture of a girl sitting and studying on her desk and chair, and there is a blackboard in front of her which reads, assume root 2 is rational. Let root 2 be equal to p upon q in lowest terms. Then p square is equal to 2q square. Next step, p must be even, which leads to q must be even, a contradiction. Think and reflect. Try to prove the irrationality of square root 3 using the approach of proof by contradiction. Will the same approach work for square root 5, square root 7, or square root 10? 3.5.2 Construction of length square root n. Think and reflect. We have observed how to obtain a line whose length is a rational number. How do we obtain lines whose lengths are irrational? For example, to construct a line segment of length square root 2 and mark its position on the number line, we may proceed as follows. Step 1. On the number line given in figure 3.11, we measure OA is equal to 1 unit and draw a perpendicular on OA through A. Page number 56. Step 2. On this perpendicular line, we mark the point B such that AB is equal to 1 unit and join the origin to B. Clearly, OB is equal to square root 2 units. Step 3. With O as center and OB as radius. With a compass, we draw an arc which intersects the number line at P. Clearly, OP is equal to square root 2 units. Hence, P represents the irrational number square root 2. Here we have figure 3.11 which explains constructing irrational lengths and locating them on the number line. We find a number line with the markings -3, -2, -1, 0, 1, 2, and 3. Distance between 0 and 1 are marked as O and A as 1 unit. Then AB is taken as 1 unit. On joining O and B, we have distance square root 2, and we have OC and BC also to be 1 units. Taking OB as the radius, we cut an arc or number line which represents point P equal to square root 2. Think and reflect. Try to extend this method for constructing line segments of lengths square root 3 and square root 5 using a ruler and a compass. Generalize this method to construct a line segment of any length of the form square root n, where n is a positive integer. 3.5.3 The Story of Pi and Madhav's Infinite Series. Another famous irrational number is pi, the ratio of a circle's circumference to its diameter. For centuries, mathematicians sought better and better fractional approximations for pi. Aryabhatta, 499 CE, gave the highly accurate approximation 3927 upon 1250, that is equal to 3.1416, but stated that this was only an asana approximation and indicated that an exact fraction could likely not be found. However, because pi is irrational, as was formally proven by Lambert in 1761, no single fraction or finitely many fractions can ever provide a perfect formula for pi. An exact formula for pi was first unlocked in the 14th century by Madhava of Sangamgrama, who launched the Kerala School of Mathematics. Madhava realized that to express an irrational number, you cannot use a single fraction. You must use an infinite sum. He discovered the profound infinite series. Pi is equal to 4 into, within brackets, 1 minus 1 upon 3 plus 1 upon 5 minus 1 upon 7 plus and so on. We know what it means to add 2, 100 or even a lakh terms. What does it mean to add an infinite number of terms? It means finding the value that we get closer and closer to as we add more and more terms of the infinite sum starting from the first term. Page number 57. You will learn more about infinite series in higher grades. Thus, the number line is not only filled with rational numbers but also contains irrational numbers. You have seen how to mark some irrationals and will simply conceive the rest of the irrationals to lie on the line. Here we have in figure 3.12 a number line marked ranging from -5 to +5, and we can find -22 upon 5 marked between -5 and -4, minus under root 10 marked between -4 and -3, minus 12 upon 5 marked between minus 3 and minus 2, minus 3 upon 2 marked between minus 2 and minus 1. We have minus 1 upon 3 marked between minus 1 and 0. Also 5 upon 6 marked between 0 and 1. We have square root 2 marked between 1 and 2, and also 3 upon 2 marked between 1 and 2. We have under root 5 marked between 2 and 3, and the value of pi marked between 3 and 4. Also 7 upon 2 marked between 3 and 4. 9 upon 2 is marked between 4 and 5 on this number line. 3.6 real numbers, decimals and cyclic patterns. When we unite the dense web of rational numbers with the unfillable gaps of irrational numbers, we create the unbroken continuous line of the real numbers R. The easiest way to distinguish a rational number from an irrational number is to look at its decimal expansion. 3.6.1 Rational decimals, terminating and repeating. If you divide the numerator of a rational number by its denominator, exactly one of the two things will happen. First one, it terminates. The division eventually leaves a remainder of 0. The decimal stops. Example 2. 3 upon 8 is equal to 0.375. Can you tell for which rational numbers the decimal will be terminating? Second point, it repeats. The division never reaches a remainder of 0, but the sequence of digits begins to loop infinitely. Example 3. 5 upon 11 is equal to 0.454545 and so on. That is equal to 0.45 with a bar on 45. Think and reflect. Try to find the decimal expansions of 10 upon 3 and 11 upon 12. What do you observe about the repetition of the digits after the decimal point? Page number 58. Why do some rational numbers have repeating decimal representations? Imagine calculating 1 upon 7 using long division. You are dividing by 7. What are the possible remainders at each step? They can only be 1, 2, 3, 4, 5 or 6. Why not 0? Because there is a limited number of possible remainders. Eventually, a remainder must show up a second time. Once a remainder repeats, the entire division process loops, creating a repeating decimal. Predicting the type of decimal expansion. The interesting thing is that we can predict whether the decimal expansion of a rational number will terminate or go on forever without actually doing the long division process. For this, we resort to finding the prime factors of the denominator. Let P upon Q, Q not equal to 0, be a rational number in its lowest terms. That is, P and Q have no common factor other than 1. Consider the fraction 3 upon 20. The prime factorization of 20 is 2 to the power 2 into 5. Hence, 3 upon 20 is equal to 3 upon 2 square into 5. That is equal to 3 into 5 upon 2 square into 5 into 5. That is equal to 15 upon 100. That is equal to 0.15. We multiply the numerator and denominator by 5 to get 100 and arrive at 0.15, which is a terminating decimal. Think and reflect. The decimal expansion of P upon Q will be terminating precisely when the prime factors of Q are only 2, only 5, or both 2 and 5. Can you explain why? This is because in such cases, we can make the denominator a power of 10 by multiplying both numerator and denominator by a suitable number. Converting rational decimals into the form P upon Q. Case 1. Terminating decimals. We have already observed in earlier grade how to convert terminating decimals in the form P upon Q. Page number 59. Example 4. Convert 0.35 into the form P upon Q. We know that 0.35 is equal to 35 upon 100 is equal to 7 upon 20. Now let us understand how to convert non-terminating repeating decimals into the form P upon Q. Case 2. Pure repeating decimals. A pure repeating decimal is one in which a digit or a sequence of digits begins repeating immediately after the decimal point. Example 5. Convert 0.6 bar into the form P upon Q. Step 1. Let x equal to 0.6 bar. Step 2. Since one digit repeats, multiply both sides by 10 is equal to 10. We get 10 into x is equal to 6.6 bar. Step 3. Subtract the first equation from the second. 10x minus x is equal to 6.6 bar minus 0.6 bar is equal to 6. Step 4. Solve for x. 9x is equal to 6. Thus, x is equal to 6 upon 9 is equal to 2 upon 3. Example 6. Convert 0.45 bar into the form P upon Q. Let x be equal to 0.45 with a bar on 4 and 5 both. Since two digits repeat, multiply by 10 to the power 2, that is equal to 100. We get 100x is equal to 45.45 bar. Subtracting the two equations, we get 99x is equal to 45. So, x is equal to 45 upon 99, that is equal to 5 upon 11. Case 3. General repeating decimals. A general repeating decimal has some non-repeating digits just after the decimal point followed by a repeating block. Example 7. Convert 0.16 bar into the form P upon Q. Step 1. Let x be equal to 0.16 bar. Step 2. First, shift the decimal to place the repeating part immediately after the decimal point. Page number 60. Since one digit is non-repeating, we multiply by 10 to the power 1 is equal to 10 and obtain 10x is equal to 1.6 bar. Step 3. Now, to prove one full repeating cycle, one digit repeating, we multiply by 10 to the power 1 is equal to 10 again and get 100x is equal to 16.6 bar. Step 4. Subtracting the first shifted equation from the second, we get 100x minus 10x is equal to 16.6 bar minus 1.6 bar, that is equal to 90x is equal to 15. Thus, x is equal to 15 upon 90, that is equal to 1 upon 6. Example 8. Convert 2.357 bar into the form P upon Q. Step 1. Let x be equal to 2.357 bar. Step 2. Here 35 is non-repeating, that is 2 digits. 7 repeats, 1 digit. Firstly, we multiply by 10 to the power 2, that is equal to 100, to move the non-repeating digits before the decimal, and we obtain 100x is equal to 235.7 bar. Step 3. Now we multiply by 10 to the power 1 is equal to 10 to move the full repeating cycle and get 1000x is equal to 2357.7 bar. Step 4. Subtracting, we obtain 1000x minus 100x is equal to 2357.7 bar minus 235.7 bar. Hence, 900x is equal to 2122 and x is equal to 2122 upon 900, that is equal to 1061 upon 450. Example 9. Convert 2.4537 with a bar on 37 into the form P upon Q. Step 1. Let x be equal to 2.4537 with a bar on 37. Step 2. Here 45 is non-repeating, that is 2 digits. 37 repeats, 2 digits. Firstly, we multiply by 10 to the power 2, that is equal to 100, to move the non-repeating digits before the decimal, and we obtain 100x is equal to 245.37 bar. Step 3. Now we multiply by 10 to the power 2 is equal to 100 to move the full repeating cycle and get 10,000x is equal to 24,537.37 bar. Step 4. Subtracting, we obtain 10,000x minus 100x is equal to 24,537.37 bar minus 245.37 bar. Hence, 9,900x is equal to 24,292 and x is equal to 24,292 upon 9,900 is equal to 6,073 upon 2,475. Summary table for conversion. We have a tabular column here which depicts the decimal type and the steps to follow. For pure repeating decimal type, we have the steps to be followed as: first one, let x be equal to decimal number. Second, multiply by 10 to the power n, where n is equal to number of repeating digits. Third step, Subtract from the original equation and solve for x. Page number 61. For general repeating decimal type, we have the following steps mentioned in the table. First step, let x be equal to the decimal number. Second step, multiply by 10 to the power m, where m is equal to number of non-repeating digits. Then multiply by 10 to the power n, where n is equal to number of repeating digits. Third step, subtract from the previous equation and solve for x. 3.6.2 The magic of cyclic numbers. When we calculate the decimal for 1 upon 7, we get 0.142857, 142857, and so on, or 0.142857 with a bar on all the digits. The repeating block 142857 is one of mathematics' most fascinating gem, a cyclic number. Watch what happens when we multiply it by the digits 1 through 6. 142857 into 1 is equal to 142857. 142857 into 2 is equal to 285714. 142857 into 3 gives 428571. 142857 into 4 is equal to 571428. 142857 into 5 is equal to 714285. 142857 into 6 is equal to 857142. The same digits simply shift in a cyclic circle. This beautiful internal structure is a hallmark of the rational number 1 upon 7. 3.6.3 Irrational decimals, chaos and infinity. Irrational numbers, however, possesses decimal expansions that never end and never repeat. There is no cyclic block, no pattern that loops forever. Examples include square root 2 is equal to 1.41422133562373050488 and so on. Pi is equal to 3.1415926535897932384 and so on. Exercise set 3.5. Question number 1. Without performing long division, determine which of the following rational numbers will have terminating decimals and which will be repeating. 7 upon 20, 4 upon 15 and 13 upon 250. Then check your answers. By explicitly performing the long divisions and expressing these rational numbers as decimals. Page number 62. Question number 2. Perform the long division for 1 upon 13. Identify the repeating block of digits. Does it show cyclic properties if you evaluate 2 upon 13? Now, compute 3 upon 13, 4 upon 13, etc. What do you notice? Question number 3. Classify the following numbers as rational or irrational. First part, square root of 81. Second, square root of 12. Third, 0.33333 and so on. Fourth one, 0.12345, 12345, 12345 and so on. Fifth one, 1.01, 001, 0001, 00001 and so on. Notice the pattern. It is repeating a single block. Sixth part, 23.5601, 8561, 2239, 874, 790, 120. Find the explicit fractions in case they are rational. Question number 4. The number 0.9 bar, which means 0.99999 and so on, is a rational number. Using algebra, let x be equal to 0.9 bar, multiply by 10 and subtract. Explain why 0.9 bar is exactly equal to 1. Question number 5. We have noticed that the repeating block of 1 upon 7 is a cyclic number. Try to find more numbers n whose reciprocals 1 upon n produce decimals with repeating blocks that are cyclic. Non-uniqueness of decimal representations, just as 1 is equal to 10 upon 10 is equal to 100 upon 100, rational numbers can have two decimal forms. Any terminating decimal has an alternative with repeating nines. 1.000, that is equal to 0.999 and so on. 2.47000 and so on is equal to 2.46999 and so on. Is it not surprising that 0.999 and so on is equal to 1? Many would have guessed that it is slightly less than 1. 3.7 Conclusion. The never-ending journey. We have traveled an immense distance from the simple notches carved into a Ishango bone to track the passing days to the profound philosophical void of Shunya in ancient India. Page number 63. We crossed the threshold of zero into the realm of depths and negative numbers with Brahmagupta. We found that the space between numbers is infinitely dense with fractions, yet fundamentally interspersed with the infinite non-repeating decimal irrational numbers like root 2 and pi. By uniting the rational and the irrational, we build the continuous, unbroken real number line. Every length, every temperature, every real physical measurement in the known universe has a home on this line. The evolution of our world of numbers. Our world of numbers has grown in stages over thousands of years to meet the needs of humanity. Natural numbers n, the basic counting numbers 1, 2, 3 and so on, these are contained in the collection of integers. Integers represented by z, these include also 0 and the negative numbers -2, -1, 0, 1, 2 and so on. These in turn are contained in the collection of rational numbers. Rational numbers represented by Q. These include all fractions P upon Q, where P and Q are integers and Q is not equal to 0. They also correspond to those numbers with terminating decimals like 0.135 and repeating decimals like 0.142857 with a bar on them. Irrational numbers represented by I. These are separate from the above. They are numbers that cannot be written as fractions. Example, square root 2, pi, square root 10 also do not have terminating or repeating decimals. Real numbers, denoted by R, together the rational and irrational numbers make up the entire real number line. In figure 3.13, we can find the representation of real numbers. Real numbers are made up of irrational numbers and rational numbers. We can find them in two different rectangular shapes. Then we have integers, which is a part of rational numbers. And again, inside the integers, we have another rectangular box representing natural numbers. Page number 64. Is the journey over? Are there more numbers waiting to be discovered beyond the real number line? Think and reflect. Consider this puzzle. What is the square root of -1? We know that 1 into 1 is equal to 1. We also know that -1 into -1 is equal to 1. There is no real number that when we multiply it by itself results in a negative number. Thus, square root of -1 cannot exist on number line. To solve this, mathematicians stepped completely off the line and invented a new dimension of numbers denoted by the letter I, standing for imaginary numbers. While they sound like fiction, they are essential for modern electrical engineering, quantum mechanics, and the technology that powers your mobile phone. But that is a journey for another year. For now, master the real numbers. The universe is largely written in their language. End of chapter exercises. Question number 1. Convert the following rational numbers in the form of a terminating decimal or non-terminating and repeating decimal, whichever the case may be, by the process of long division. First part, 3 upon 50. Second part, 2 upon 9. Question number 2. Prove that square root 5 is an irrational number. Question number 3. Convert the following decimal numbers in the form of P upon Q. First part, 12.6. Second part, 0.0120. Third part, 3.052 with a bar on 52. Fourth one, 1.235 bar on 35. Fifth one, 0.23 bar with a bar on 23. Sixth one, 2.05 bar with a bar on 5. Seventh one, 2.125 with a bar on 5. Eighth one, 3.125 bar with a bar on 5. Ninth one, 2.1625 with a bar on 1625. Question number 4. Locate the following rational numbers on the number line. First part, 0.532. Second part, 1.15 with a bar on 5. Page number 65. Question number 5. Find 6 rational numbers between 3 and 4. Question number 6. Find 5 rational numbers between 2 upon 5 and 3 upon 5. Question number 7. Find 5 rational numbers between 1 upon 6 and 2 upon 5. Question number 8. If x upon 3 plus x upon 5 is equal to 16 upon 15, find the rational number x. Question number 9. Let a and b be two non-zero rational numbers such that a plus 1 upon b is equal to 0. Without assigning any numerical values, determine whether AB is positive or negative. Justify your answer. Question number 10. A rational number has a terminating decimal expansion whose last non-zero digit occurs in the fourth decimal place. Show that such a number can be written in the form p upon 10 to the power 4, where p is an integer not divisible by 10. Is it necessary that the denominator of this rational number, when written in the lowest form, is divisible by 2 to the power 4 or 5 to the power 4? Give reasons. Question number 11. Without performing divisions, determine whether the decimal expansion of 18 upon 125 is terminating or non-terminating. If it terminates, state the number of decimal places. Question number 12. A rational number in its lowest form has denominator 2 to the power 3 into 5. How many decimal places will its decimal expansion have? Explain your answer. Question number 13. Let A be equal to 7 upon 12 and B be equal to 5 upon 6. Express both A and B in the form K1 upon M and K2 upon M, where K1, K2 and M are integers and K2 minus K1 is greater than 6. Using the same denominator M, write exactly 5 distinct rational numbers lying between A and B, keeping an integer numerator. Explain why the condition K2 minus K1 is greater than n plus 1 is necessary to find n such rational numbers between the two rational numbers A and B using this method. Question number 14. Three rational numbers x, y and z satisfy x plus y plus z is equal to 0 and xy plus yz plus zx is equal to 0. Show that all the rational numbers x, y, z must be simultaneously 0. Page number 66. Question number 15. Show that the rational number a plus b upon 2 lies between the rational numbers a and b. Question number 16. Find the lengths of the hypotenuses of all the right triangles in figure 3.14, which is referred to as the square root spiral. Here in figure 3.14, we have a beautiful colored picture of square root spiral with units expressed as 1 unit for the construction of the square root spiral, giving square root 2, square root 3, square root 4, square root 5, square root 6, square root 7, square root 8, square root 9, square root 10 and square root 11 as the length of the hypotenuses. Chapter summary. In this chapter, you have learned the following concepts. Natural numbers, represented as n, are the counting numbers 1, 2, 3, and so on that emerged at least tens of thousands of years ago due to humanity's need to count. The concept of zero, shunya, was formalized in India by philosophers and then brought into mathematics formally by Brahmagupta 629 CE, who transformed the philosophical state of nothingness, shunyata, into an actual number on which one could perform arithmetic operations. Brahmagupta also introduced the negative numbers, that is, numbers less than 0. Integers, represented by z, extend the number line to the left of 1 to include 0, as well as the negative numbers, which Brahmagupta historically categorized as debs, ren, in contrast with the positive number fortunes as dhan. Page number 67. Brahmagupta's laws provided the first rigorous framework for arithmetic with signed numbers, establishing rules such as the product of two debts is a fortune, minus into minus is equal to plus, as well as the rules for zero. Rational numbers represented by Q are defined as any number that can be expressed as a ratio P upon Q, where P and Q are integers and Q is not equal to 0. Brahmagupta also gave the formal rules for addition, subtraction, multiplication, and division of rational numbers. Rational numbers are dense, meaning a rational number always exists between any two other rational numbers. Irrational numbers are values like square root 2 and pi that cannot be written as fractions. Their existence proves that the number line contains gaps that rational ratios alone cannot fill. The first proof of the irrationality of a number was that of square root 2 by Hippasus c. 400 BCE. It was a proof by contradiction, a proof that pi is irrational as it was suspected to be by Aryabhatta in 499 CE, was given by the Swiss mathematician John Lambert in 1761. Real numbers, represented by R, represent the total union of all rational and irrational numbers, forming a perfectly continuous and unbroken line where every real physical measurement has a corresponding point. Decimal expansions serve as a mathematical signature for rational versus irrational. Rational numbers always result in terminating or repeating decimals, while irrational numbers produce non repeating decimals that continue infinitely. Cyclic numbers, such as the digits found in the repeating block of 1 upon 7, that is 142857, reveal the elegant and symmetrical internal patterns hidden within the rational numbers. Imaginary numbers are introduced as a final conceptual frontier to handle operations like square root of minus 1, which cannot be solved on the real number line and require a new dimension of mathematics. Chapter 3 ends here.
Ganit Manjari, Part 1. You were just listening to this audiobook, Textbook of Mathematics for Grade 9. Narration, Swarnlata Sharma. Sound recordist, Mohammad Faizan Khan. Assistance in production, Mukul Singh. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.